Hey guys, Mr. Butts here. I want to talk to you about something called a slope field. Slope field is something that we're going to use to kind of give us clues using a differential equation about what the function or a solution to the differential equation might look like. So I want to start with just what a slope field is. It's going to be a graphical representation of some differential equation, but it can only represent what the solution is going to look like at a finite number of points. And essentially, what we're going to do is we're going to take a coordinate plane and we're going to look at different points in the coordinate plane and look at the slope of the function or what the solution might look like at that point. So if we're given some differential equation, this is a differential equation because it has a derivative in it. What we can do is we can pick a point and we can say, okay, at that point 2, 2, what's the slope of the solution going to be if the solution goes through the point 2, 2? So one thing to understand about a slope field is that it's going to represent information about lots of different solutions to a differential equation because we're asking the question, what would it look like if it goes through that point? So we don't know that a solution is necessarily going to go through the point at 2, 2. So if I take, for this particular example, the point 2, 2 and plug in, really all we need here is the y value, then we would get dy dx at the point 2, 2 is going to be 2 times 7 minus 2, which is 5 over 10, and that would just give us a slope of 1. So on our slope field, we are going to see just a little tick mark, long enough to see, but not so long that it's going to extend too far beyond the point, a slope of 1. And we're going to do that not just at one point, but at lots of different points. As you can imagine, doing this by hand would get pretty tedious, but using technology can give us graphs that look like this. So this is the differential equation. You can see that at the point 2, 2, the one that I did by hand, we see a slope that looks like a slope of 1. But the computer was able to, for me, give me the slopes at lots and lots of different points. Doing this by hand would take a really, really long time, but technology can help us and allow us to see what a graph is going to look like. So what we're going to do then is we're going to throw in what's called an initial condition. We're going to say, okay, if the graph of this function goes through the point 0, 1, so we might say that if f of x is a solution to this differential equation, and we know that f of 0 is equal to 1, then what's the graph of that going to look like? Well, these slope lines are going to give us a clue as to what the graph is going to look like. So we can see that at this point here, if we move off to the right, it's going to be moving in about that direction. But as we move to the right, you can see the slopes are getting steeper. So a graph that follows these slope lines might look something like this. And as we go to the left, you can see the slope lines are decreasing, so we might get something that looks like that. So the slope field allows us to kind of see how a solution to a differential equation will flow through a coordinate plane. If we throw in, by the way, technology is pretty good at giving us solutions to differential equations also. So this graph was given to me by a grapher on my computer. If we throw in a couple other initial conditions, we could kind of get an idea of what solutions might look like through those points. So it looks like we might get things that look like this. The initial condition here at B, it's kind of hard to tell exactly what's going to happen just from our slope field. It looks like it could just look like this. We're not going to see sharp corners on something like this because the function is differentiable, which means that we're not going to get corners, which would be points that are not differentiable. In order to handle that, we might throw more points in there. And again, technology is great at this. Creating a slope field like this by hand would literally take days probably to do. But with a slope field like this, it's easier to see what a solution is going to look like through more of a variety of points. So again, with technology, I can graph those and see what they would look like. Notice that all of these solutions have asymptotes with a horizontal line of y equals 1. I think that might kind of make sense because as the function gets closer to a y value of 7, the derivative is going to get closer to a slope of 0. and we do end up with a horizontal asymptote there. Also, we do end up with horizontal asymptotes going to the left, at least for these two initial conditions at y equals 0 for the same reason. I just wanted to show you that using technology, we can get more and more points. However, if you remember at the very beginning, I said it's going to be for a finite number of points. We can never look at every single point in a coordinate plane and know exactly what the slope's going to be. The more and more points that we use, the more and more accurate we can guess at what a function is going to look like as we move through the slope field. But a slope field is just giving us an idea of how a solution is going to move through a coordinate plane, but cannot give us a complete picture. So I want to take just a few more points as an example and kind of look at how we might create a slope field ourselves. If you are asked to do a slope field by hand, to create one by hand, you're not going to be asked to do more than a few points. Now, I will ask you to do more than 3, but I'm not going to ask you to do a slope field that has 100 points in it, which would be 10 by 10 or something like that. So just looking at this one here, I'm going to just jot down my work next to each point. So the slope at the point 3, 2, we already did the math for this one, because really the only thing that's relevant is the y coordinate. So plugging the 2 in for y, we get 2 times 5 over 10, which is 1. So we would expect a slope of 1 at this point. When you're creating a slope field, it's not that important that your slopes are exact. I did aim for, if I continue here, I aim for that point because I know a slope of 1 is going to go through the point 1, 0 from 3, 2. But if it's a little bit off, that's okay. It is important that if you have slopes that are steeper, that they look steeper. If you have positive slopes, they should definitely be positive slope or negative or 0. Those kinds of things you should be able to control to some extent. For the slope here at 0, 5, dy dx at 0, 5 is going to be so 5 times 7 minus 5, which is 2 over 10. So that also gives us a slope of 1. I did choose some points that were going to be a little bit easier. If we plugged in a y value of 4, we would have 4 times 3, which is 12 over 10. So it'd be a slope of 1.2. So it should just look a little bit steeper. So like, for example, at this point, it should just be a little steeper than the slope at y equals 5. If we plug in the 0.57, the y value going in for, or 7 going in for the y value is going to give us 7 times 0 over 10, which is 0. And you may remember from looking at the graph that the slopes along the y value of 7 were all 0 slopes. And that's because when we plug 7 in for y, we get 0. So again, I plotted slope lines for 3 points. This is something you should be able to do for a few points, up to maybe 12 or 15 points, but I'm not going to ever ask you to do more than that. And I also won't ask you to do a lot for a complicated differential equation. One last thing I want to mention about these slope fields is that they cannot give us a complete picture of what a solution to the differential equation is going to look like. So in the example here, I have 2 different slope fields for the same differential equation. And you'll notice, first of all, that this differential equation has a solution that we should know. If the derivative of a function is secant squared of x, that function could be tangent of x, because the derivative of tangent is secant. And so this as a solution does flow nicely through both of these. But I want to point out that the slope field on the left has vertical lines, or at least very close to vertical lines. We're never going to get vertical lines in a slope field because the slope of a vertical line is undefined. We wouldn't plot undefined slopes, but we get very close to vertical lines, and so our tangent curve flows nicely through there, and we see that we have vertical asymptotes. However, in the other slope field, where those vertical lines would be, we don't have, and so it would be reasonable to think that a solution in this this coordinate plane right here, this slope field, might look something like this, and just go right through where we know there is a vertical asymptote. So slope fields are good at giving us hints about horizontal asymptotes like we saw in the last example, vertical asymptotes like we see here, but they're not perfect. Since we are only looking at slopes at a finite number of points, we might be missing some important information. So it's important that we know enough about what we're trying to do that we know what kind of information might be missing and account for that when we are doing problems involving slope fields.